Now, can everybody see that?
Yeah.
Okay, so this is just a proof that I have been in Kerala before. This is from my visit in 2010 that Vijay was telling you about. And before I start, I would like to just say one thing. As Vijay said, there are many, many open problems. I will be mentioning quite a number of them. I hope you'll get interested and work on them, but I also hope that you will stop at me and ask questions if you need to, anywhere, anytime during the talk, or you can save them up to the end. So you can either interrupt and ask a question, or you can put them in the chat, except that I can't see the chat, so somebody else will have to keep an eye on that for me. But I will try and take a little break every now and again to let you just catch up with the ideas and to see if there are any questions. So with that said, I suppose it's time to, well, let's have a little bit more eye candy before I start the lecture proper. Here is a lovely picture by Scott Harper, a former undergraduate student in St Andrews. He's now at the University of Bristol. This is the generating graph of the alternating group of degree 5. So the vertices are the non-identity elements of the group, and you join two vertices with an edge if they generate the group. And this is an example of a very important class of graphs, one of the types of graphs that I will be telling you about in these lectures. So feast your eyes on the generating graph of A5, and as the time comes up to 5:30 Indian Standard Time, I will begin. So I must first of all thank Vijay. I'm absolutely delighted to be opening this seminar with two talks. It is an auspicious occasion, and I very much hope, as Vijay said, that we will solve some of these open problems and write some papers and enjoy ourselves, basically. So now, graphs and groups is a very big subject, and I am not going to tell you about everything. So geometric group theory, much of algebraic graph theory, aspects of computation such as the graph isomorphism problem, finite and infinite permutation groups, all of these things have aspects that come under the heading of graphs and groups. So this is a huge topic, but I'm going to just take one bit of it. And Vijay mentioned this paper of mine on the archive. When I put it on the archive, it was 75 pages. It's now gone up to 80 pages and continues to grow. So there will be a new archive version sometime, maybe next week. But I'm talking about essentially the content of that paper, but going beyond it in various ways. So this is the general situation. G is a group, usually a finite group, but sometimes I'll mention infinite groups. And gamma will be a graph whose vertex set is G, or possibly some large subset of G, and whose edges reflect the group structure of G. So if you have met before the commuting graph, where you join two elements x and y if xy is equal to yx, or the power graph, where you join two elements x and y if one of them is a power of the other. And of course, there is also the generating graph, the example of which we just saw on the previous slide, where you join x and y if the two elements x and y together generate the group G. So I will be talking about those graphs and some others and posing a number of questions. But I'm not just talking about these graphs as isolated graphs. They really form a hierarchy. So I will give you 5 graphs where each one is contained in the next. And so we're going to be doing a comparative study of these graphs, looking at common properties, looking at how they relate to one another and the differences between their edge sets and things like that. So that's going to be my focus in these 2 talks that I will be giving. So this is an outline of what I hope to get to in these two talks. I will introduce this hierarchy of graphs on a group, describe a few of their properties, develop some graph theory to help study them. So I found that since I started on this project, I've discovered various facts about graphs which I was just not aware of before, particularly concerning cographs and twin reduction in graphs. And I want to spend some time explaining that to you because it is actually very relevant to the kind of graphs that I'm talking about here. Relate them to other interesting graphs that people have looked at. There's the Grunberg-Kagel graph, sometimes known as the prime graph of a group. Intersection graphs, where the vertices are not elements of the group, but subgroups, and you join them if they have non-trivial intersection. And I want to pose a number of open problems, but perhaps most importantly, I want to provide you with some tools to study these problems. So this is what I'm hoping to cover in this series of talks. And in particular, I just mentioned cographs. I will spend some time on cographs, defining them. They go by many other names. You may have met them under a different name. I will define them, show you why they're important for our problem. They have a very rich structure theory, and I will pose the question for which groups G is one of the graphs associated with the group G, let's say the power graph or the commuting graph, a cograph. I think these are interesting and important problems. They connect also with the study of the automorphism groups of these graphs, because I will describe to you my first encounter with the automorphism group of the generating graph of a group. I was absolutely shocked to find that the automorphism group of the generating graph was much, much, much larger than the group that I started off with. There is a reason for that, and understanding cographs and twin reduction helps us get a handhold on that. So that is one of the things that I will spend some time on in these lectures. Okay, so here's the preprint. That's the archive number. As I say, the version on the archive now will be superseded fairly soon by a new version. I will tell you some of the new things that will go in the course of these lectures, but there will be others as well. So, there is a problem with notation if you talk about groups and graphs, because if you go to a lecture on group theory, the lecturer usually begins by saying something like, let G be a group. If you go to a talk about graphs, the lecturer will start off by saying, let G be a graph. And we would get enormously confused if both our groups and our graphs were called G, especially when the graph is built on the group. So we have to make a decision. And I'll tell you the decision I made and why I made it. The word graph comes originally from Greek, and so it makes sense to use a Greek letter for a graph. So my graphs will typically be called gamma. Group is a German word originally, and so a group should probably be a Gothic G, which looks like that. Now, I don't know about you, but I was never taught how to write a Gothic G in handwriting, and I just would find it very difficult taking notes if that letter came up too often. So I'll tell you a little story about that from my time as a student many years ago. I had to read Heinz Lüneburg's book about the geometry of the Mathieu groups. His book was in German, and the groups were all called things like Gothic G. So I had not only to figure out how to reproduce these symbols in my notes, but also to learn enough German to translate his mathematical German into English. It was actually very clearly written, so I had no problem. But I had not studied German before that, so that was my introduction to German. So anyway, the upshot of all this is that G will be a group, gamma will be a graph. And usually, the vertex set of gamma will either be G or some large subset of G, as we will see. Now, there's another problem with notation too. People have studied the graphs that I'm talking about, usually individually. So people write papers about, let's say, the commuting graph. The commuting graph has a long history going right back to the 1950s. The power graph, the generating graph, these things have been around for a while and people have written papers about them, and they tend to use one-off notations like script G of the group or gamma of the group or something like that. If I'm not going to do that because I'll be talking about several different kinds of graphs on the same group. And I don't expect you to remember whether curly G is the power graph or the commuting graph or whatever. So I'm going to use notation like this. The power graph of G will be power of G. The commuting graph will be com of G. And the other graphs that I introduce will have similar names. The generating graph will be gen of G. So I hope that will make it easier to remember at any moment which particular graph I will be talking about. So, as I introduce each type of graph, I will tell you what my notation for it is. Right, so that's notation. So now I'm going to start introducing the graphs. And the other thing I should say before I leave this notation slide is, if you take one of these graphs, let's say the commuting graph, some people define the vertex set of the commuting graph to be the whole group. Some people say no, because one of the interesting questions about the commuting graph is whether it's connected or not. If you take the whole group, then of course elements in the center of the group commute with everything. So they are vertices joined to everything else in the graph. And to ask questions about connectedness, it makes sense to remove those. And so one of the important questions about each type of graph that I introduce will be, which are the vertices that are joined to everything else, or possibly which are the vertices that have no neighbors? And then if we're asking about connectedness, we have to remove them. But for many of the questions I ask, it's not necessary to do that. For example, I mentioned cographs. It will turn out that if a graph is a cograph, that property is preserved by removing isolated vertices or removing vertices joined to all others. So it will make no difference. So the default is that the vertex set of the graph is the whole group. And if I need to throw some vertices out, I'll talk about the reduced graph, and I will try and tell you on each occasion exactly what are the vertices that I will be taking out. Okay, right. On to the business. So the rest of the notation will be standard, but please stop me and ask if there's notation that you don't understand. So actually that might be a good point to just take a minute's break and say, does anybody have any questions so far? No, apparently not. Okay, let's press on. So the first graph I'll talk about is the commuting graph. So this appeared first in the famous paper of Brouwer and Fowler on centralizers of involutions back in 1955. So this was essentially the first step in the long road that took us to the classification of finite simple groups. Brouwer and Fowler proved in that paper that you could only have, if you fixed the centralizer of an involution, then there were only finitely many simple groups that could have that involution centralizer. And so that suggested a program of attack on the simple groups where you classify them by centralizer of involution. So the very first paper towards the classification is this paper of Brouwer and Fowler in 1955, and they used the commuting graph. So the commuting graph has the vertex set G. Two vertices, little g and little h, are joined if they commute. So exactly what you would expect. But there is one small subtlety here. The definition I just gave you would actually say a vertex commutes with itself. G times G is equal to G times G. So every vertex would have a loop. Usually we don't want loops. So for the most part, I will suppress the loops. And here is an example of a commuting graph. So this is the commuting graph of two different groups. You see, the commuting graph of an abelian group is rather trivial. It's just the complete graph. But so here are two small non-abelian groups, the dihedral group and the quaternion group of order 8. And in fact, if you take the standard descriptions of these groups generated by two elements A and B satisfying some relations, it turns out that you get exactly the same labelings of the vertices. So that the commuting graphs of these two groups are isomorphic, and the isomorphism is just label the vertices by the elements in these groups if they're described in this way. Now, you can probably see that the vertices, the identity and A squared, I have colored in red. They are the elements which form the center of this group. They commute with everything. And the other vertices don't. They fall into three sets of two, which are joined to everything in the center as they should be, and to one another, but to nothing else. So the graph is connected, but if I threw away the center, it would become disconnected. It would fall into three disjoint components. So that's an example of the commuting graph. And as I said, I would call it COM of G. So the commuting graph is COM of G. The next, possibly not the next graph to be defined, but the next one that I'm going to talk about is the power graph, which was defined by Kolarov and Quinn in 1999. And it's really a directed graph, but we're going to forget the directions. And so I want to talk a little bit about the theory of it. So the directed power graph is a directed graph on the vertex set G. So I put a directed arc from G to H if H is a power of G. So I join an element to its square and its cube and
Sorry,
so
can
on.
I ask a quick question, please?
Yes, of course. Yes.
Could you go back to the previous slide?
Yes.
If you remove the, so it looks to me like the three components you would get when you remove the center are three cosets of the center.
That's absolutely correct. Yes, yes, that is. And indeed, you can see if the graph decomposes as much as it can, it will be into cosets of the center. Usually that doesn't happen. But if you take the center, the elements in the center commute with everything. So if you take the element A, well, it commutes with itself, it commutes with the elements in the center, but it also, if you multiply it by an element of the center, it will commute with that. So you see that in any coset of the center, everything commutes. So when you remove the center, that will be a complete subgraph. So in the worst case, those will be the connected components. But in many other cases, there are more edges and the structure is much richer. But this is just a simple example, but you're absolutely right. In this case, the cosets of the center are playing a very important role. Yes, thank you for the question. Is that okay?
Yeah.
Okay,
yes.
So back to the power graph. So the directed power graph has an arc from G, a directed arc from G to H, if H is a power of G. And once again, we ignore loops because G is a power of itself. So technically there should be a loop, but we just ignore it. The power graph, you just simply ignore the directions. So you put an edge from G to H if there's an arc between G and H in the directed power graph. But you have to also say one other thing. It might be that G is a power of H is a power of G and G is a power of H. There might be arcs in both directions between G and H. Then I simply put in the power graph, I put a single edge connecting G and H. So I don't worry about whether they're joined one way or both. I just simply undirect the power graph and delete multiple edges. So that's the power graph. Now, the power graph doesn't uniquely determine the directions. Let me just talk you through an example of this. If you take the cyclic group of order 6, in the cyclic group of order 6, there are two, if it's generated by an element little a, there are two generators, a and a to the 5th. And there's also the identity. Now, a and a to the 5th generate the group, so everything else in the group is a power of each of those elements. So they have edges going out. They are sources. They have edges going out to all the other vertices. Whereas the identity is a sink. It's a power of any element. And so it's joined to everything else, but all the edges go in. But if I just give you the power graph, not the directed power graph, you will see those three vertices. They're joined to everything else in the graph. You won't know which is the identity and which are the generators. So you can't recover the directions uniquely, but you can recover them up to isomorphism. If two groups have isomorphic power graphs, then they have isomorphic directed power graphs. So you can recover the directions up to isomorphism, and this will be useful later on. So that's the power graph. And if you go back to that example, it is the power graph of the Quaternion group because all the elements outside the center have order 4. So a cubed is a power of a and a is a power of a cubed. The elements in the center are also powers of a and a cubed. So you see all these really are edges in the power graph. But in the dihedral group, there's a cyclic subgroup of order 4, but the other elements are just involutions. So these edges joining them to a squared and to one another will not exist. They will only be joined to the identity. So these groups have isomorphic commuting graphs, but they don't have isomorphic power graphs. Now I want to go to the next graph, which the name I will use for it is the enhanced power graph. Now, the complementary graph of this was first defined in 2007 by Abdullahi and Hassan Abadi. I didn't learn about this. Sorry?
So can you go to previous theorem, whether the converse of the theorem will hold or you have some counterexample?
Yes, the converse is certainly true, yes, because if I know the directed power graph, I get the power graph just by forgetting the directions, right? So that's true, that's true, that's the easy way around. The more difficult way is going from the finding the directions if you're not given them initially.
Okay, thank you.
Okay?
Yeah,
so
fine.
If you have the directed power graph, you get the power graph immediately. If you have the power graph, you don't. And in fact, I do not know a simple algorithm to put those directions back. That's an open problem if anyone wants to tackle it. But they are determined. We know that they're determined. So there is, in principle, an algorithm which would say, try all the directions and see which one works. But I would like a nice algorithm. I don't have one. So there's a nice open problem there.
Sorry, could you phrase that question once more, please?
The question is the following. The theorem says if two groups have isomorphic power graphs, they have isomorphic directed power graphs. And that means if I hand you a graph, which is the power graph of a group, but I don't tell you the group, you can't tell the group, but you can tell the directed power graph. So in other words, you can somehow construct a directed graph, which is the directed power graph of that group. So the question is, find an algorithm to do that. So I hand you a graph, which is the power graph of a group. Your task is to put the directions on the edges to make it the directed power graph of that group.
Yeah, but the undirected power graph there could be many groups that give rise to the same.
Yes, They will, but they will all give you the same directed power graphs. That's what this theorem says. If two groups have isomorphic power graphs, then they have isomorphic directed power graphs.
Okay.
So there may be many groups, yes, there can, but there is only one directed power. There's only one, up to isomorphism, there's only one directed power graph.
Well,
All
it
these
seems
groups,
it seems to me there is a related question where if you're
Yes.
given the undirected power graph, can we find at least one group for which this is the power graph?
that's a very good question, yes. If you could find it, just one group of which it was the undirected
Then we can
power
solve
graph,
this problem maybe.
then you can solve the problem because you can just take the directed power graph of that group. Absolutely correct. Yes, thank you. Yes. So that would be one way of going about it. If you want to find an algorithm, the algorithm might say, do this and find a group that has that power graph and then take its directed power graph. But there may be other ways of doing it without actually identifying the group. I don't know. But okay, so we've already come across, this early in the talk, we've already come across what looks like quite a rich and interesting open problem.
It's a very interesting problem.
So thank you for all that. That's
nice. Peter?
Yes?
So you gave
Sorry?
one example of a group where the power graph and commuting graph coincide.
Coincide. Yes, the Quaternion Group does that.
Yeah. So can we say anything in general about that?
That's another excellent question. I can say something about that, and I will later on in the talk.
Okay,
So
okay.
It's coming up. It's coming up.
Okay, fine.
Okay, so the enhanced power graph. So Abdullahi and Hassan Abadi defined something they called the non-cyclic graph of a group. And that's actually just the complement of what, in this paper by Alipur et al., we called the enhanced power graph, because it's the power graph with some extra edges. And this is the terminology I'm going to use. So the enhanced power graph, which will be E power of G, is the graph that has vertex set G. We join G to H. In the power graph, remember, we join them if one of them is a power of the other. Now I'm going to say we join them if, in this new graph, if there's an element K such that both G and H are powers of K, right? So you see, if one of them is a power of the other, if G is a power of H, then I can take K to be H, and both G and H will be powers of that element. So every edge in the power graph is an edge in the enhanced power graph. But we can phrase that in a different way. G and H are joined in the enhanced power graph if and only if the group that they generate is cyclic. Because if they're both powers of an element K, that means they both lie in the cyclic group generated by K, but we know that every subgroup of a cyclic group is cyclic, and therefore the group generated by G and H will have to be cyclic. So another way of defining the enhanced power graph is to say we join two elements if and only if they generate a cyclic group. So that's the enhanced power graph. And now, the power graph determines up to isomorphism the directed power graph. But the directed power graph determines the enhanced power graph, because you see, if you know the directed power graph, take two elements G and H. I want to know when to join them in the enhanced power graph. Well, I look to see if there's a K that sends arcs to both G and H. In other words, if G and H have a common in-neighbor in the graph, in the directed power graph, then they're joined in the enhanced power graph. So if I know the directed power graph, then that determines the enhanced power graph. And therefore, the power graph determines the enhanced power graph up to isomorphism. But once again, not absolutely, because of this problem that you can't distinguish the identity. But the converse is also true. This is a recent theorem by Zahirovic, which I haven't actually even read the proof of myself yet. But if two groups have isomorphic enhanced power graphs, then they have isomorphic power graphs. So up to isomorphism, any groups that have one of these graphs isomorphic, will have all the others isomorphic, the directed power graph and the enhanced power graph. But they needn't coincide precisely. But anyway, so that's the enhanced power graph. Now, the last one, this is a little bit more mysterious. We only did this very recently. So Boyan Kuzma and I have a paper on the archive which defines this thing that we call the deep commuting graph. Now, the deep commuting graph, this is the rule. The vertex set is G once again. And when do I join two vertices? Well, in the commuting graph, I join them if they commute. But I'm going to put a tougher requirement on them here. They're joined if and only if they're inverse images in every central extension of G commute. Now, what I mean by that is if you have a group H, which has a subgroup contained in its center, such that H over Z is isomorphic to G, then you see elements of G correspond to cosets of Z in H. So if I take G and H in the group G, and I let AZ and BZ be the corresponding cosets of Z in H, and I ask whether A and B commute, and whether this is true in every central extension. Now, we already had a little discussion about this. If you take a subgroup in the center, then if you take any coset of it, if the elements in this coset, if one element in this coset commutes with one element in this coset, then every element here commutes with every element here. So it doesn't depend on the particular choice of coset representatives here. It appears to depend on the central extension, but in fact, one of the things we showed is that there's one central extension that will do the job and tell you about the deep commuting graph, and this is something called a Sure cover. Now, what we do is we take this subgroup Z to be not only in the center of H, but also in the derived group of H, so in the intersection of the center of H with the derived group, the commutator subgroup of H. And subject to that, Z should be as large as possible. Now, Sure proved that if you put those conditions on, then Z is uniquely determined up to isomorphism. It's called the Sure Multiplier of G, and it has various interpretations, including in homological algebra. It's the first homology group of G over the integers, or the first cohomology group over the roots of unity. It also has a description in terms of a presentation of G. I'm not going into any of that, but if you just take a Sure cover and say, okay, take the Sure cover and use this rule here, G and H are joined in the deep commuting graph if and only if their inverse images in the Sure cover commute, then that will define the same graph. It doesn't depend on the choice of Sure cover. The Sure multiplier Z is unique, but the Sure cover is not necessarily unique. I'll show you an example in a moment. And these, but the graph that you get on G doesn't depend on which Sure cover you take, and also it satisfies these conditions for the deep commuting graph. So let me just go back again to that example we had of the dihedral and Quaternion groups. This is the commuting graph of the dihedral group and also of the Quaternion group. Now, if you think about the Klein group of order 4, the group C2 cross C2, it's Sure, well, it has two Sure covers. They are precisely D8 and Q8. And this is the commuting graph of D8 or Q8. And as we discussed earlier, the four cosets of the center are clearly visible in this picture. And so now, when we work out the deep commuting graph of the Klein group, so we take the Sure cover, which is one of these, and then we sort of project it back down onto G. In other words, imagine this picture and look at it from above so that A and A cubed coincide, 1 and A squared, so that it just coincides. What will you see? You'll see a star. You'll see a vertex in the center with 3 edges radiating out from it. So the deep commuting graph of the Klein group is a star, whereas the ordinary commuting graph, of course, is the complete graph because it's an abelian group. So that's an example of the deep commuting graph. I admit it is more complicated to understand, quite a bit more complicated to understand. I won't be saying...
Sorry to interrupt. Can we
go ahead, please.
Can we think of the commuting graph as a covering graph of the deep commuting graph? It seems to be the case.
The commuting graph of the Sure cover is a cover of the deep commuting graph of the original group. Yes, that's absolutely right. Yes.
Okay.
Yes, thank you. Yes, and that picture, keep that picture in mind because that shows you exactly what's happening. Okay. The general case is no more difficult than the case I showed you.
Okay, thank you.
Okay. Now, so here we are. The Klein group of order 4 has two Sure covers, the dihedral and Quaternion groups. And if you look at that, you see that they cover the star K13, which is then the deep commuting graph of V4, whereas the commuting graph is the whole of K4. Okay, so that's the commuting graph.
Peter, can I
yes.
ask a question? I mean,
yes, please.
We saw that the commuting graph of the dihedral and the Quaternion groups were the same, and
yes.
they're both Sure covers of the Klein 4 group.
Yes.
I mean, what I'm asking is because the commuting graph of the Sure cover has to be a cover of the
deep commuting graph of G.
Of the deep commuting
yes.
graph. Will that
yes.
mean that the commuting graphs of the Sure covers will be the same always?
Yes. Yes, they are. Yes, that's right.
Okay.
You can take any two Sure covers of the same group. Their commuting graphs will be isomorphic. That's right. That's absolutely right. Yes. So if you get this paper that Boyan and I wrote, it's all spelt out in there. That's got proofs of all these things that I'm saying.
Okay.
Right. So that's the deep commuting graph. And as I said, I won't say quite as much about that as I did about the, as I will about the others. But so finally, here's the non-generating graph. I've told you about the generating graph, but for reasons which you will see very soon, I really want to talk about the non-generating graph of G. That is the complement of the generating graph. So I join two elements in the non-generating graph if and only if they don't generate the group. Right? So it's just the complement of the generating graph. And let me just remark here that one consequence of the classification of finite simple groups is that every non-abelian finite simple group can be generated by two elements. So there'll be some pairs of elements that generate and some pairs that don't generate. So both the generating graph and the non-generating graph of a finite simple group will be non-trivial. Of course, there are less interesting cases. Suppose that you have a group that can't be generated by two elements, needs at least three generators. Then there are no edges in the generating graph. The non-generating graph is the complete graph. So there are less interesting examples, but we'll see things like this later on. There are several other graphs that have been studied, and that's enough for us to be going on with now. Okay, so I just want to say a little bit about one thing. The generating graph is different from the others in one, or the non-generating graph in one respect. If you take any of the following, the power graph, the enhanced power graph, the commuting graph, call that X. So X means com or power or E power, and restricted, take the induced subgraph on a subgroup of G, then it's just the corresponding graph of that subgroup. Because in all cases, whether or not two elements are joined is the same in the subgroup as it is in the whole group. If they commute in the whole group, they commute in the subgroup. If one's a power of the other in the whole group, then it's a power of the other in the subgroup, and so on. So all those are properties that go down very nicely to subgroups. The non-generating graph is a little bit different, because if you restrict the non-generating graph to a proper subgroup, two elements in that proper subgroup cannot generate the whole group because they're contained in a proper subgroup. And therefore, the non-generating graph is the complete graph on this subgroup. So you take an interesting group with an interesting non-generating graph. As soon as you restrict it to a proper subgroup, you get the complete graph. So that's a very different behavior from what happens in these cases. And for the deep commuting graph, it's even more complicated because the Sure multiplier behaves in a very erratic way as you go from a group to a subgroup. So just to warn you about those. Now, really the reason why I'm talking about these graphs is because, as I said, they form a hierarchy. Edges of the power graph, if two vertices are joined in the power graph, they're joined in the enhanced power graph. I showed you that at the time. If they're joined in the enhanced power graph, they're joined in the deep commuting graph. And if they're joined in the deep commuting graph, they're joined in the commuting graph. So the edge sets of these graphs, each one is contained in the next, so they form a hierarchy. Yeah, and all of these are clear. The requirements for being joined in the deep commuting graph, as I said, are tougher than they are in the commuting graph because you have to commute in every central extension. So it's clear that the edge set of the deep commuting graph is a subset of this one. So what isn't perhaps immediately clear to you is why the edge set of the enhanced power graph is contained in the edge set of the deep commuting graph. So here's a little proof. Suppose that you have G and H are joined in the enhanced power graph. Remember what that means? That means that the group that they generate is generated by one single element, K. So now we're trying to prove that they're joined in the deep commuting graph. So we take a central extension of G and let Z be the central subgroup of H, so that H over Z is isomorphic to G. And so G, H, and K are no elements of G, so they correspond to cosets of Z in H. And if we call these, if we take coset representatives A, B, and C, then what do we know? We know that the group generated by Z, A, and B is also generated by Z and C. That comes from this equation here. Remember that these G, H, and K are now cosets of Z in H. Now, we said earlier on that if you take a central subgroup of a group and one more element, then everything in the group they generate commutes, because C commutes with all the elements of Z and they commute with one another. So this is an abelian group, and therefore it contains A and B, therefore A and B commute. That's true for every central extension, and therefore G and H are joined in the deep commuting graph. So that's why that step in the hierarchy works. But we can take the hierarchy one step further. In most interesting cases, if G is either a non-abelian group or a group which is not two generated, then the edge set of the commuting graph is contained in the edge set of the non-generating graph. So if it's either non-abelian, if it's non-abelian, then two elements that commute can't generate G because G is non-abelian, so then they're joined in the non-generating graph. If G is not two generated, then we saw that its non-generating graph is complete, so that this is clear. So we can put the non-generating graph above the commuting graph in this hierarchy in every case except where G is an abelian group with at most two generators. And we can complete the hierarchy by putting the complete graph at the top and the null graph at the bottom. And when we do that, we've built a hierarchy, so we can say, when are two of those graphs equal? And I already had a question about when the commuting graph is equal to the power graph, which I'm now going to answer. So here are some answers. Here are some answers to that question. The power graph is equal to the null graph if and only if G is the trivial group. If G is not the trivial group, take any non-identity element. The identity is a power of it, so there's at least one edge. So the power graph is the null graph if and only if G is the trivial group. The enhanced power graph is equal to the power graph if and only if G contains no subgroup CP cross CQ for distinct primes P and Q. Well, you see, CP cross CQ is isomorphic to the cyclic group generated by an element of order PQ. So both the generators of these two are powers of the element of order PQ. But they're not powers of one another. So they're joined in the enhanced power graph, not in the power graph. And it's a fairly easy exercise to prove the converse. So that's a criterion for the enhanced power graph to be equal to the power graph. Here's a criterion for the commuting graph to be equal to the enhanced power graph. It's that G contains no subgroup CP cross CP for a prime P. So this was for distinct primes P and Q. This is just for a single prime. You see, in CP cross CP, these two elements commute. These generators of these two CPs commute, but neither they don't generate a cyclic group. So there's no element such that they're both powers of it. So they're not joined in the enhanced power graph. If G is a non-abelian group, then the non-generating group is equal to the non-generating graph is equal to the commuting graph if and only if G is a minimal non-abelian group. That is, a non-abelian group, all of whose proper subgroups are abelian, because two elements that fail to generate a proper subgroup. If all the proper subgroups are abelian, those two elements will commute, and so the non-generating graph will be equal to the commuting graph. And once again, the converse is also true. And finally, the non-generating graph is complete if and only if G can't be generated by two elements. So the last condition is easy to understand. The first condition is easy to understand. I will say a little bit more about the three in the middle. Groups not containing CP cross CQ for distinct primes P and Q. These are groups in which every element has prime power order. They've been studied for quite a long time, but only recently is there a complete classification. So my paper with Natalia Maslova on the archive has a complete list of the groups with this property. So they're the groups for which the power graph is equal to the enhanced power graph. Groups not containing CP cross CP, well, by a theorem that goes back to Burnside, these are groups for which all the Celoff subgroups are either cyclic or generalized quaternion. And there are known classification theorems that tell you what those groups are. So they're essentially all known. And the ones where the commuting graph is equal to the non-generating graph, the minimal non-abelian groups, these were determined way back in 1904 by Miller and Moreno. So this is quite a classic result. So the groups with the commuting graph equal to the non-generating graph.
I'm sorry to interrupt.
Yeah, go ahead.
What does a generalized Quaternion group look like?
What does it? Well, you know what the Quaternion group looks like.
Yes.
So for the generalized Quaternion group, in the Quaternion group, let's say it like this: you have an element of order 4 that generates a cyclic subgroup of order 4. Then you have another element that conjugates that to its inverse, but which also has order 4. Now, in the generalized Quaternion group, you relax the very first condition. The first element you take has order an arbitrary power of 2, greater than or equal to 4. So it's generated by an element whose order is an arbitrary power of 2 greater than or equal to 4. A second element of order 4, conjugation by the second element inverts the first element. So that's generalized Quaternion group. It's a particular case of what are called dicyclic groups in theory of Cayley graphs. Now, the deep commuting graph, there are conditions for it to be equal to the ones on either side of it in the hierarchy, either the enhanced power graph or the commuting graph, but this is more complicated to state, so I think I will refer you to the paper by Boyan Kozma and me. And now, Vijay, you told me that I was to talk for 45 minutes, but I'm still I'm about halfway through the material that I prepared for the first lecture. Would you like me to go on a little bit longer?
Yeah, we can have for 15 minutes more.
Okay, I will go on for a bit longer. I will try and get to the point where I'm about to define cographs, and we might leave that for the second lecture. That sound sensible?
Yes.
Okay, right, so I'll press on with this for a bit. So Bogomolov multiplier, what is this? It's something that was first invented in the theory of invariance, and there's a conjecture of Noether about the transcendence of invariance. It was invented to handle that question. You don't have to know anything about that to know what it is, but there is a description of it in my paper with Kuzma, and also you can compute it, because there's a nice gap package called HAP, which will compute the Bogomolov multiplier of a finite group. So it's not quite as mysterious as it might first appear. So now I come to differences. We have a hierarchy, so it's very natural to ask about the differences. Suppose you look at, you take two of these graphs in the hierarchy and say, what about the graph where the edges are the ones that are joined in the larger, but not in the smaller, right? So for example, I could, well, here's a trivial example. The difference between the power graph and the null graph is just the power graph. And the difference at the other end of the hierarchy, the difference between the complete graph and the non-generating graph is just the generating graph. And of course, both of these graphs have been studied. But what about others? You might, for example, say, well, the power graph and the commuting graph. Build a graph whose edges, x and y, are joined if x and y commute, but they're not powers of each other. So that's the difference between the commuting graph and the power graph. We know when that graph has no edges, because we talked about when two of the graphs in the hierarchy were equal. But what about the differences? Well, Saul Friedman has worked on this, and there will be detailed results about the difference between the non-generating graph and the commuting graph in his thesis. And I believe he's also going to give a talk in this research seminar, so I think he might tell you about some of that stuff then. So I won't say any more about that, but except that there's a whole raft of problems here, because take any two graphs in the hierarchy and look at their difference and ask graph theoretic questions about it, connectedness, induce subgraphs, and so forth. Other cases are open, so I mentioned the commuting graph minus the power graph. So choose your favorite graph theoretic property or parameter and look at one of these graphs and see what you can say about it. Plenty to do there, but I don't want to spend more time on that, because I want to get on to, I want to at least say something about universality. So I'll talk about universality, and then I'll stop for today and carry on with cographs tomorrow, which is, I hope, going to be one of our big topics. So universality. A graph is universal if it contains every graph in some class as an induced subgraph. So which graphs can be embedded as induced subgraphs in various graphs in our collection? So if we start with the power graph is not a universal graph because the power graph of any finite group is the comparability graph of a certain partial order. And therefore, all its subgraphs, all its induced subgraphs are comparability graphs of partial orders. I will say briefly about why this is true. So if you remember the directed power graph, you join x to y by an arc. You have an arc from x to y if y is a power of x. That relation is not quite a partial order. It's what's called a partial pre-order. In other words, it's reflexive and transitive, but it may not be antisymmetric. But it will have, so a pre-order, a partial pre-order, you can define an equivalence relation by saying two things are equivalent if if each is less than or equal to the other in the partial preorder, then you get equivalence classes. The equivalence classes are partially ordered. So to extend to a partial order on the whole group, all I have to do is put a total order on each equivalence class. So there's a simple construction. It's spelt out in my manuscript, and it shows you that these are comparability graphs of partial orders. This is a very important class of graphs, incidentally. According to Dilworth's theorem, these graphs are perfect. I'll say a bit more about perfect graphs later on. So these are perfect graphs, but every finite graph, which is the comparability graph of a partial order, is an induced subgraph of the power graph of some group. So they're not universal, but they're universal for comparability graphs of partial orders. On the other hand, all of the other types in the hierarchy is universal. If you take any finite graph, you can find a finite group G for which it's an induced subgraph. So you can embed any finite graph in the enhanced power graph of a group, or in the commuting graph, or the deep commuting graph, or the non-generating graph as an induced subgraph. You can find a group that will do that. And the constructions are different in each case. So I won't go through them now, but there's a question. Find a good upper bound for the order of a group G such that every n-vertex graph is an induced subgraph of the power graph or commuting graph, or whatever you like to take. And so if you take this one, the first question says, take a graph on n vertices and find a group which might depend on the graph you took. But the second question asks something tougher. It says, find a group that embeds every n-vertex graph. And in fact, just this morning, I've made an advance on my previous result on this. If you take, so for a given value of n, there is a group with 3 to the power 2n plus 1 vertices, elements, so a group of order 3 to the power 2n plus 1, whose commuting graph contains every n-vertex graph as an induced subgraph. And it's a well-known group, actually. It's the extra special group of plus type. So it's the central product of copies of the non-abelian group of order p cubed and exponent p for any odd prime p. But so if you take p equals 3, you get the smallest. So that's new hot news about that problem. And
Peter,
so,
can I ask a question?
Yes.
I don't know if it's silly, but if you take the complete graph on the n vertices,
yes,
and if you can see it as an induced subgraph of the power graph or commuting graph or something of G, would that automatically imply that any other n-vertex graph would also be an induced subgraph?
No, because I did carefully say induced subgraph. So for the induced subgraph, you take only those edges that are already there. So if you can embed the complete graph, that's a good thing to do, because that gives you a lower bound for the clique number and stuff like that. But on the other hand, I want to embed every graph actually as an induced subgraph, so that edges go to edges and non-edges go to non-edges. So I am asking more than just embedding complete graphs. Yeah. Now, I got these two the wrong way around. It's one that's the tougher condition, because here I want a group that embeds every n-vertex graph. Here I allow the group to depend on the n-vertex graph. And I had a bound of 2 to the n plus 1 for that. Well, as I said, I've now got a bound of 3 to the 2n plus 1. For the other question, I can embed every n-vertex graph as an induced subgraph in the commuting graph on of a group of order 3 to the 2n plus 1. So I haven't written this up yet, so you'll have to wait for that. But it's not a difficult argument. It only takes a couple of paragraphs, and the group is, as I say, the central product of non-abelian groups of order p cubed and exponent p. So a simple construction. So
the first
I think
construction, the first construction, the group is a kind of universal group for which.
So this one here, it says, if you give me a graph on n vertices, I can find a group of order 2 to the n plus 1 whose commuting graph embeds that graph.
Right.
But the other one says, I can find a group on 3 to the 2n plus 1 of order 3 to the 2n plus 1 such that every group of order n embeds. So the second question just asked, for each group, you're allowed to choose a different graph. And that's indeed what I did with this bound. But the first one says, I want a group that works for every graph. Now, I had a much worse bound before, because you see, if you take all the groups on n vertices, all the graphs on n vertices, there is a graph that embeds them all. It's a Paley graph on an exponential number of vertices. I forget the exact function. So there is a graph on 2 to the 2n or something like that vertices that embeds every n vertex graph as an induced subgraph. And then you just have to embed that in the commuting graph or power graph of a group. But I've been able to do it much more economically by using a bit more group theory here. So that's the situation. Right. Are there any more questions? Well, as I say, I'm going to stop there.